Today we're going to be doing a calorimetry laboratory exercise where we're going to be trying to identify the specific heat capacities of different metals. Now, we're going to start by discussing what is calorimetry briefly, and then we're going to move into how we're actually going to perform this lab. There are a lot of different types of calorimeters that we can use, but in this case we're going to use a very simple one. We're going to call it a coffee cup calorimeter because it's made of, well, a coffee cup. And this coffee cup calorimeter is going to be used to be able to determine the energy flow between two different things in this situation. Now, anytime we're talking about calorimetry, we're talking about being able to measure, quantify the amount of energy transferred into or out of a system and into or out of a surrounding area. And we use the calorimeter itself as the surroundings. So in this case, the calorimeter is going to be filled with water. We're going to have a discussion as to what that means and how we're going to be able to use it. Within calorimetry, what we are measuring is the change in the temperature of the surrounding. Now in the surrounding region, we're going to have water and the calorimeter itself. What that means is we need to measure the delta T, the change in temperature. And we're going to plug that into an equation where Q, or heat, is equal to M, mass, times C, specific heat capacity, times that delta T, change in temperature. It's really important that you keep in mind what the mass is, what the specific heat is, and what the change in temperature is relative to what is actually changing temperature. In this situation, in this lab, we're going to be placing a hot metal into a coffee cup filled with water. In this situation, we're measuring the change in temperature specifically of our water and of the metal. Each of them is going to change temperature. So we need to make sure we keep this equation correct such that when we're looking at the change in temperature of the water, that we're also accounting for the mass of the water and the specific heat of the water. When we're looking at change in temperature of the metal, we're accounting for the mass of the metal and the change in temperature of the metal. Let's briefly discuss specific heat capacity. Now, the specific heat capacity of a substance is the amount of energy, oftentimes in joules, that it's going to take to change 1 gram of that substance by 1 degree Celsius. Another way of saying it is 1 joule per gram Kelvin, because remember, 1 degree in Celsius is equivalent to 1 degree in Kelvin. So we can change the temperature in either Kelvin units or in Celsius units, and it doesn't matter. As long as it's change in temperature, we can use either value. The key here is that you need to understand that with specific heat capacity, a higher specific heat capacity, a greater magnitude value, means that it takes more energy to change the temperature of a substance, and a lower specific heat value, one that's closer to 0, is going to be fewer joules required to change the temperature of that substance, or less energy. One thing to be careful of, specific heat capacities can never be negative. It always requires energy to increase the temperature. You can never have negative energy and increase the temperature of a substance. The overarching objective of this lab is to identify the specific heat capacities of unknown metals, and then try to identify the metals based on their specific heats, which is an intensive property. It's a property that is inherent to the metals that we're going to be examining. Now, in this process, what we're going to do is we're going to use heat transfer from the metal into water in order to calculate this. In order to do that, we need to understand that energy is conserved. Heat gained by the water is equal to the heat lost by the metal. A way of thinking about this is Q, which is how we look at heat, is equal to negative Q. So Q of the metal is equal to negative Q of the water, or Q of the water is equal to negative Q of the metal. In other words, heat gained by one thing is equivalent to the heat lost by the other. One assumption we're going to make in this situation is that the energy transfer is perfect. One thing that we can run into issues with is if the energy of the calorimeter is going to be not 0. So in other words, if I have a hot cup of coffee, I feel, if I grab it, heat. That means energy is leaving the coffee cup. So coffee cups aren't perfect calorimeters, but they do a good enough job insulating for the time that we're looking at and the change in temperature that we're looking at, that we're going to assume that the heat capacity of a calorimeter in this case is 0. In other words, it's a perfect, seen kind of what needs to be done. Let's think about possible sources of error. First of all, remember how I was telling you that we needed to make sure that the energy of the boiling water was fully transferred into the metal. This required us putting the metal into the water for an extended period of time in order to make sure that was transferred. If for whatever reason the metal did not reach 100 degrees Celsius, that's a potential source of error. Also, as we are moving the metal from the boiling water into the coffee cup calorimeter, it could have cooled down slightly. That also could be a source of error. And finally, another source of error is if we had an imperfect calorimeter. By imperfect calorimeter, what I mean is that it would be a calorimeter that's not absorbing either all of the energy evenly, or it itself is absorbing some of the energy out of the water itself. So in other words, we have a situation where it's not a perfect transfer of energy from the metal to the water, and some of that energy actually ended up in the calorimeter itself. So two different ways we could have an imperfect calorimeter. But that was why it was so important that we kept stirring the water and that we made sure that we really quickly saw the change in temperature before it.
Now we're going to look at the specific heat. Specific heat is defined as the amount of heat required to raise 1 gram of a substance 1 degree Celsius. For example, water has a specific heat of 4.184 joules per gram per Celsius degree. We have a piece of cadmium metal, and we're going to try to find out the specific heat of this metal. We know that the quantity of heat is equal to mass times the specific heat times the change in temperature. So let's start by finding the mass of our sample. The mass of our sample is 58.953 grams. What we're going to do is we're going to heat this sample to 100 degrees, or approximately 100 degrees. We'll get the exact temperature. And we're going to take 100 milliliters of water at room temperature. So let's measure 100 milliliters of water. Remember that 1 milliliter of water is 1 gram. So if we know that we have 100 milliliters, then we know that we have 100 grams. And this is at room temperature. So we know that when we put this hot metal in there, it's going to gain heat. We're going to use our coffee cup calorimeter because it's insulated. And we're going to assume that it gains no heat, and the water gains all of the energy that's given off by our metal. So let's find the temperature of our water, and the temperature is 22 degrees Celsius. And we have our water boiling, so we're going to tie a string to our sample so that it doesn't touch the bottom of the beaker. If it touches the bottom of the beaker, then we don't know for sure what the temperature is. But if it stays in the water, then we know that the metal will be the same temperature as the water temperature. Let's put our thermometer in the water, about the same height, and then we'll lower everything in the water together. Okay, and we're going to let this boil long enough that we know that the temperature of the metal is the same temperature as the water. I think we've waited long enough to be confident that our metal and our water are at the same temperature. Our temperature is exactly 100 degrees. So I'm going to take out my thermometer, and I'm going to take my sample, and I'm going to quickly put it in the water. Put the top on, swirl it around, and we're going to swirl the cadmium metal in the water with a thermometer to try to make sure that we get uniform temperature. We'll read our thermometer, and when it stops changing, we'll record that temperature. And it looks like it's steady at 25 degrees C. So that means we have a 3-degree temperature change. So you now have the temperature change in the water, the temperature change in the metal, and the mass of the metal. So your task is to calculate the specific heat of our cadmium metal.